So here we've got a quantity z, and it's a function of two variables, x and y, although only the variation with x is shown on this graph. Here's a point and an associated rate of change at that point. And notice that we've used the partial symbols here because z is a function of x and y, even though there's only the change with respect to x being shown here. And let's imagine that we want to ask the question, how much effect does a small change in x here have on z? And we'll call that small change in z delta z in the same way that delta x is a small change in x. Now, if the green tangent line were a good representation of the curve for z, then this would be the change in z over that small change in x, and it would be given by an expression using the rate of change. So the change in z is the rate of change of z with respect to x multiplied by whatever change in x we have. And that's really similar to things we've seen before when we've calculated changes in displacement as velocities multiplied by a time interval. That's what we've been doing. But the thing is, if the blue curve for z is not well approximated by the green tangent line, then actually there's a difference between the change in z as calculated from the green tangent line and reality. And the reality then includes an error or a residual, if you like. This epsilon represents how far away from the truth your calculated change in z will be by taking it off a tangent line. And so the true change is shown in red, and it has this added residual. So what's the point of showing you all this? Well, quite often in physics you'll hear phrases like, if x changes by a small amount, or for small changes in x. And quite often that's because things are being approximated by a constant rate of change. So what's happening is that a curve might be like the blue line, and we're describing it like the green tangent line. Now the green tangent line you can see here is a good approximation to the blue line, but only for really small values of delta x. And if we shrink delta x down to infinitesimal values, then the fit to the blue line gets better and better. We can use dx, called a differential, to stand for an infinitesimal change in x, and in that case the corresponding change in z, called dz, which is the differential in z, will be given by that expression there, and that is the definition of the differential in z.